Let's look at linked state routing. Specifically, we will discuss the linked state routing algorithm of choice, called Dijkstra's algorithms. It was conceived by computer scientist Edgar W. Djikstra in 1956. He first demonstrated this algorithm by solving the best path problem for driving between cities in the Netherlands. When the algorithm is finished running, all the nodes in the network will have a complete map of the network with all the nodes and all the costs of all the links. This information has been learned by all nodes sending out linked state broadcasts. Let's examine this algorithm. The algorithm finds the shortest or least cost path from a source node to all other nodes in the network. The algorithm runs k times to find the best path to k different destinations. Once the algorithm finishes, the forwarding table for that source node has been computed. To describe the algorithm formally, we use a specific notation. We have a set of destination nodes N. When we have found the least cost path for each one of these nodes, we move it to another set, the visited set, called N prime. As discussed previously, for the link cost from node X to node Y, we'll use the notation C of X, Y. For the tentative lowest cost of the path from the source of the destination node V, we'll use the notation D of V. For the predecessor node, we use the notation P of V. Node X is said to be the predecessor of node of Y if a link leads from node X to node Y. On this slide, we have the pseudocode for the algorithm. We can walk through this algorithm to solve the least cost path from source node to all other nodes in our diagram. For initialization, start at source node U. Place U in the set of visited nodes N prime. If a node is directly connected neighbor of U, then assign the distance or cost of that link as the tentative distance. For all other nodes, write down infinity to represent that we do not yet know their distances from U. Next, enter the main loop of the program. Here we are going to have an educated guess that the least cost path from the source to the destination will go through the node with the least cost from U. So, select the node with the smallest distance or cost and call it the current node. Then move this current node into the visited set. Now examine all the unvisited neighbors of the current node and calculate their tentative distances going through the current node. Compare the newly calculated tentative distances to the current assigned values and assign the minimums as the new tentative distances. Loop back to step 8. Select the next unvisited node with the smallest tentative distance and make it the new current node. Continue this process until all nodes have been visited and all links examined. Let's solve another shortest path first problem using Dijkstra's algorithm. In the initialization phase, start at source node U, which is placed in the visited set N prime. Assign costs to the neighboring nodes V, X, and W, which are 2, 5, and 1 respectively. In the first iteration, look among those nodes not yet added to the set N prime and find the node with the least cost at the end of the previous iteration. That node is X with a cost of 1, and X becomes the current node. X is added to the set of visited nodes N prime. Line 12 of the linked state algorithm is then performed to update the tentative distance for all nodes, yielding the results shown in the second line in the table. The cost of the path to V is unchanged. The cost of the path to W, which was 5 at the end of the initialization, through X is found to have a cost of 4. Hence, this lower cost path is selected, and W's predecessor along the shortest path from U is set to X. Similarly, the cost to Y through X is computed to be 2, and the table is updated accordingly. In the second iteration, nodes V and Y are found to have the least cost paths with a cost of 2. We'll break the tie here, selecting y as the new current node. Add y to the current set in prime, so that in prime now contains u, x, and y. The cost of the remaining nodes not yet in prime, that is nodes v, w, and z, are updated via line 12 of the link state algorithm, yielding the results shown in the third row of the table. For the third iteration, select node v, which had been tied with node y as the least cost path, but it had not been selected as the new current node. Add v to the current set in prime. Now the algorithm examines the unexplored path from v to w. This newly examined path does not give a minimum cost. The least cost path is still through y at a total cost of 3. Repeat the process for nodes w and z. In this case, calculating the minimum cost through these remaining nodes does not change the forwarding table. The resulting graph and forwarding table are shown on this slide. In Dijkstra's, all nodes that are not yet examined in the set of examined nodes must be checked. That requires n times n plus 1 over 2 comparisons, which means that the complexity algorithm is O of n, where n is the number of nodes. Now this can be reduced to O of n log n by using a binary heap. There is a problem that can occur with all routing algorithms that use traffic load or delay as a link cost. In this case, the link cost will not be symmetric. This defect can result in oscillations in the lowest cost path selection. The 4 diagrams on this slide demonstrate this pathology. In diagram A, nodes B and D each originate a unit of traffic destined for node A. Now node C sends an increment of traffic equal to E to node A. Initially, node C is sending traffic to A counterclockwise through B. After the next link state computation, diagram B, node C sees that the clockwise path through B to A is a lower link cost than the counterclockwise path. Node B sees the same thing, so B and C reroute traffic clockwise. The link state algorithm runs again, diagram C. And now nodes B, C, and D detect a zero-cost route in the counterclockwise direction. These nodes now reroute their traffic counterclockwise. Then the next time the link state algorithm runs, diagram D, nodes B, C, and D detect a zero-cost route in the clockwise direction and reroute their traffic accordingly. These nodes now reroute their traffic counterclockwise, and so on. These nodes now reroute their traffic counterclockwise, and so on and so on. We could prevent this oscillating behavior if the link cost is not based on traffic loads. But this is not a good solution since one goal of routing is to avoid very congested links. There is another solution. Make sure that all routers do not run the Dijkstra's algorithm at the same time, and randomize the time each router sends out its link state advertisement. In the next video, we will look at the distance vector algorithm.